A network router's primary function is to interpret the destination address of an incoming data packet and determine the best path for transmission. It evaluates the physical layer for signals, the data link layer for frames, and the network layer for IP addresses to move packets from a source to a specific destination. Data warehousing applies these same structural principles to coordinate the movement of records from high-velocity production servers into long-term repositories. The engineering challenge is organizing millions of disjointed operational transactions so they can be retrieved by an executive dashboard without slowing down the active system. This chart shows the three-tier data warehouse architecture. It creates distinct boundaries for storage, processing, and application delivery. The bottom tier handles data extraction. It pulls raw information from active databases, standardizes the formatting, and stores it in a central repository. The middle tier is the processing layer. It uses online analytical processing, or OLAP, to reorganize flat storage tables into multidimensional logical structures. The top tier is the front-end layer. It hosts the decision support systems and visual interfaces that users rely on for predictive modeling. Implementing these three tiers prevents analytical queries from competing for the same hardware resources used by live transactions. This separation of concerns allows the enterprise to scale its storage and its analysis independently. The data journey begins at the edge of the network, where operational source systems generate raw transactional records. Many enterprises utilize NoSQL databases, like MongoDB, for these tasks because their schemaless design allows for extremely high-velocity data ingestion. Because these systems distribute data across multiple server shards to scale horizontally, they require internal routing interfaces to manage client requests. This diagram shows the MongoDB routing architecture. The Mongo service consults the config server to locate metadata, routing requests to the correct shard. There, records are stored as BSON documents, encapsulating related attributes into a single nested object, rather than spreading them across tables. BSON is efficient for writing individual records, but analyzing billions of these unstructured documents is computationally expensive. This data must be routed into a staging area for processing. Within this staging environment, the data undergoes ETL, extract, transform, and load. During the transform phase, the system scrubs noise, resolves missing values, and converts mismatched data types into a uniform schema. The load phase then pushes this cleansed data into its permanent analytical home. That destination is the data warehouse repository, a consolidated, non-volatile database designed strictly for read-heavy analysis. Unlike the operational NoSQL shards that focus on current states, the warehouse is time-variant. It stores years of history, allowing for the identification of long-term trends. Physically separating the operational NoSQL environment from the historical warehouse ensures that intensive analytical scans do not cause latency for the end users of the live application. With the data unified in storage, we enter the middle tier, where flat records are translated into logical analytical models. Standard relational tables are difficult to query across multiple axes simultaneously. To calculate trends across product lines, regions, and time periods, specialized OLAP servers are required. These engines reorganize the data into multidimensional structures to minimize query latency. One approach is multidimensional OLAP, or MOLAP. A MOLAP system pre-calculates and stores every possible dimensional intersection during the initial data load. These values are stored in proprietary cubes. Because the answers are computed ahead of time, retrieval is nearly instantaneous. However, pre-calculation can cause a sparsity problem, where the system wastes disk space storing empty intersections for dimensions that have no associated data. For larger, more granular datasets, architects use ROLAP, relational OLAP. ROLAP avoids proprietary cubes entirely, leaving the data inside the relational database engine. To maintain performance, ROLAP relies on a star schema layout. The center is the fact table, holding quantitative metrics like revenue and units sold. Surrounding it are dimension tables containing descriptive attributes like product categories, allowing the engine to filter facts without complex table joins. The ROLAP engine dynamically translates user requests into nested SQL joins against this star schema as needed. This makes the middle tier the critical bridge between flat historical records and high-speed business analysis. Finally, the data reaches the top tier, the front-end presentation layer. Here, the primary objective is to feed a decision support system, or DSS. Managers use a DSS to address semi-structured problems where standard reports are insufficient. It utilizes the process data to build predictive models. This diagram shows the internal subsystems of a DSS. The data management subsystem pulls metrics from the OLAP servers. That data moves into the model management subsystem, containing mathematical forecasting algorithms used to project outcomes. Finally, the user interface allows executives to run what-if simulations, changing input variables to alter long-term trajectories. In healthcare, administrators use this to forecast emergency room traffic. By analyzing admission logs and local demographic data, the DSS predicts surges in patient volume. These predictions are possible because the incoming data was standardized in Layer 1 and dimensionally indexed in Layer 2. From the NoSQL edge through the ETL pipeline and into the star schema, every step of this journey is designed to deliver a single integrated view of the enterprise. This three-tier routing protocol allows an organization to coordinate its institutional knowledge the same way a network router coordinates packets. By isolating analytical workloads from operational databases, engineers ensure that high-frequency writes and complex read queries never interfere with each other. This structure creates a single source of truth, ensuring that every department is making decisions based on the same consolidated history. The physical distribution of the NoSQL shards provides the raw capacity, while the logical structure of the star schema provides the speed. Efficient data routing is what enables an enterprise to turn billions of raw, distributed records into a reliable roadmap for the future.